flow. The reason why this is important is manifold. One, we saw even in not the first lecture but the second lecture that if we look at Poisson flow, that this scales with the characteristic length scale of the device. And so if we made the device twice as big, the average velocity of Poisson flow would go up by a factor of 4. We did not see the same thing when we had a Couette flow, which was a surface-driven flow. And so the relative magnitude of surface-driven flow to pressure-driven flow tends to get bigger and bigger as we go down to small scales. And so that means that anytime we have a surface-driven flow, an interface-driven flow, we might expect this to be very important at small scales. Secondly, we can make an empirical observation that the systems that we use to make microfluidic devices, if you put some water in them, will always generate a voltage difference in between the bulk fluid and the wall. So if I take a glass and I pour water into it, and I had a very, very small, very, very precise voltmeter, and I put 1 voltmeter next to the wall and 1 voltmeter in the middle of the glass, I would measure a voltage difference, in that case of about 85 millivolts. If I, instead of making that out of glass, I made it out of a plastic, and I did the same thing, I might measure 60 millivolts. But in all these cases, this voltage difference is real, repeatable, and important. We'll show today that the presence of this voltage difference then also leads to a velocity difference between the flow that's very close to the wall and the flow that is some distance away from it. And we'll define that in terms of what's called the Debye length. The big picture of what we need to do to understand this, to get a handle on it, is we first need to do some quick review of electrostatics. And what we want to get out of our review of electrostatics is an understanding of two things. One, first of all, how does a source charge affect the distribution of the electrical potential, which I'm denoting as phi? So this is how does charge affect electric field. And then we also want to know, if we have some charge, what is the volume, and this charge is in a fluid, what is this volume, what is the volumetric force on that charge suspended in this fluid? So if I have charge, I know something about the potential. And if I have potential, it acts on the charge. Now, both of these two things are closely related, and they're both very important. The reason why they're going to be important in today's lecture is that we're going to come up with our first derivation of electroosmotic flow. And this derivation of electroosmotic flow is basically going to start with a simple version of the Navier-Stokes equations, where we're going to do two different things. We're going to add a term to the Navier-Stokes equations that will be a volumetric force on the fluid in the presence of an electric charge. And then furthermore, we're going to say, well, wait a second, there's some stuff we might not know about this flow, but we can use what we know about the relation between charge and electrical potential to put this equation in a form that's very easy for us to integrate. By doing that, we'll be able to come up with our first solution for electroosmotic flow, which is basically electroosmotic flow at a surface in a semi-infinite medium.